Hello, my name is Patrick Eigler. A little bit about myself. I was actually a third generation plumber. So I've been born and bred into the water industry here in the United States. I work for Crystal IS in upstate New York, and I'm joined by my co host and colleague, Dr. Richard Morita. A slightly different background. Richard's originally from Kenya and has now moved to the US, and we've joined forces here at Crystal IS, which is an Asai company. At Crystal IS, we grow world-renowned aluminum nitride substrate. We've been able to grow the largest spools, substrate, and wafer in the world, and we harness those to build UVC LEDs with some of the highest power and output. This presentation was also put together by Dr. Rajul Randiv, who is another colleague at Crystal IS. So what we're going to talk about today is retrograde bacterial contamination and the need for point of dispense UVC radiation for contamination. So what is retrograde contamination? Retrograde contamination refers to contamination that occurs at water outlets, such as taps and shower heads. Contamination ensues in the opposite direction of water flow. So water comes out of an aerator or a dispensing device, and splashback, accidentally or deliberately, can cause growth of microbial biofilms and cause retrograde contamination of the water system. This also occurs in public spaces, on aerators or points of dispense that are common to be touched. If you think about a bottled water dispenser or a water dispenser at a hospital, airport, or any public location. What happens is that initial surface attachment can happen from the cells on your skin or in the water. Over time, there's cell proliferation. That's a tough word. Proliferation. Eventually, a matrix is formed, and mature biofilms can grow back into the system, contaminating the water supply. So this contamination can be caused by mold. At times, it could also be caused by bacterial contamination. It's due to bacteria or mold that's contained in dust, which can be spread many times through accidental touch. This can happen when washing your hands, or as we talked about before, splashback. You'll often see this on nozzles or spigots. A lot of times the mesh that's actually used for aerators is a great bed for growing bacteria or mold. Microorganisms can multiply and then travel upstream in the water system, causing issues in the filter matrix earlier in the system, or just growing biofilm in the pipes themselves. I'll let Richard describe a little bit about the consequences of retrograde contamination.
Thank you, Patrick. Actually, retrograde contamination is not without cost. It can be very costly, actually, to the extent that sometimes in water systems that have been contaminated by pathogenic microbes, the situation can be as worse as experiencing fatalities. For instance, what we know now from the blood transfusion industry, if platelet bags are contaminated, and it is very easy for them to be contaminated, you can have vancomycin resistant organisms like VRE being able to contaminate the bags, and retrograde contamination can occur to the extent that we're going to give patients blood that is contaminated. Now, that's not good news, because they are going to have a situation called bacteremia, and they are going to go into shock, and they will die. And one of the most notorious organisms in the water industry is Pseudomonas aeruginosa and total coliforms. These two groups of organisms are able to grow very fast, and within a period of 24 hours, they make copious amounts of biofilms in the system. Some homes have been studied, and what we know now is that even if you have activated carbon treatment devices in your system, actually that does not prevent organisms like Pseudomonas aeruginosa from coming in and colonizing your system due to retrograde contamination. We are even surprised that even if you have a little bit of chlorine what we call the residue chlorine, which is like 0.3 milligrams per liter in your system, you can still have these organisms being able to grow because they are resistant to these chemicals as well. So that's why we strongly need some alternative strategies to be able to combat retrograde contamination.
So the common prevailing perception is that filtration can prevent this issue. So although the use of activated carbon in point of use helps the taste by removing residual disinfectant, heavy metals, or other byproducts, it comes with risk. These filters are often not designed to remove bacteria. Two, they also remove the chlorine, which is the natural or added protection for the water system. Even if it's designed to remove bacteria, filtration can encourage the growth of these microbes and colonizers once there's retrograde contamination. So in simplistic terms, if bacteria or mold can enter the water system at point of dispense, grow biofilm back into the system, the activated carbon block, often its mesh structure is a great home for the bacteria in the system. We've seen this in a few different studies coming out of China, the University of Arizona, and different university studies to prove that this is something that happens on a regular basis. So retrograde contamination with Legionella or Legionnaire's disease causing pathogens is probably one of the most dangerous components of this because eventually it can be aerosolized by the point of dispense aerator. This is an example in dental unit water lines. So if you think about a dentist's office, the splash that can be caused by retrograde can grow into the plumbing system and ultimately cause the opportunity to expose patients to Legionnaire's disease. As you can see in some of the photos here, kind of the mesh-like structure that we use in the water and plumbing industry to create uniform flow patterns also makes a perfect lattice structure for biofilm to grow. So mold and biofilms in drinking water systems, there's plenty of examples of black fungal biofilm formation, which has the ability to be linked to contamination as a means to entry. Biofilm from fungi can cause superficial mycosis. These have been detected in water systems and taps. So how does the industry, the water industry, the plumbing industry, how do they solve this issue? So mainly in public dispensing locations, there's a couple different ways to handle this issue. So one is superheating the element. So the ability to superheat your point of dispense to eliminate anything growing on the surface, whether it be bacteria or mold. The other option is to periodically flush with a hot water source. So there's certainly an energy consumption here and a waste. There's also a safety risk with both of these issues. So periodic cleaning with chemicals is the most common way to handle this, particularly in public locations, but also in residential properties. So manual cleaning can be time consuming and expensive. The trades labor element of that, and also in a public space, knowing how to time your cleaning methodology with usage can be difficult. So one of the things that we'd like to quickly introduce or discuss is the advancements in UVC technology, particularly the growth of LED development, has proven a safe and effective method, which we're going to introduce, that is at low cost and also saves quite a bit of time, energy, maintenance, and carbon to be able to provide protection at point of dispense. The following UVC LED innovations have really enabled an LED to be available, have the life, and actually protect the system from this retrograde contamination in growth. So one of the things is the germicidal wavelength being finely tuned to 260 to 270 nanometers, which is the optimal germicidal wavelength to eliminate the RNA and DNA of bacteria and biofilms. Power output greater than 80 milliwatts. So the industry as a whole, growing better substrates, investing in LED technology has allowed the industry to grow from a nascent 10 milliwatt output to 100 milliwatts plus. For many of these single LED, long life, port of dispense applications, there's a threshold of 50, 60, 80 milliwatts that can be used for system design to allow a single LED to provide disinfection performance. And the longer life and on-time capabilities really allow these system designs to implement it right at point of dispense and not have to have a maintenance cycle. Previous technologies would have to be changed out on a yearly basis. LED life has extended over 10,000 hours to the point where in effective system design, the LED will last the life of the system. We've mocked up a useful way of being able to integrate a single LED into point of dispense for relatively low cost to be able to prevent this growth of retrograde contamination. The most logical initial use cases in this are point of dispense in public locations where lots of people are touching the point of dispense, in healthcare, in dental, and in any area that bacteria or microbial ingrowth will cause major problems. Some key benefits. So in only 3 minutes per day, adding an LED to point of dispense can provide up to 4 log reduction, protection of either mold or certain known bacterias. These designs can be easy to integrate. This is our take on it. I'm sure people on the call are thinking about different ways to integrate a single LED into point of dispense. The biggest thing here is this design, for example, is safe and compliant to NSF, FDA, CE, and all the exposure requirements. One of the big parts of integrating UVC into your equipment, device, or plumbing system is the safety of the end user. And as you can imagine, the cost of adding a single LED at point of dispense to prevent this issue much outweighs the cost of your plumbing system ingrowing, causing problems, and getting people sick in the public. So there's a very small energy consumption. So one of the sustainability benefits is the spend, cost, and environmental consumption of cleaning, transporting to locations to be able to clean. This can ensure a very small energy consumption, a very efficient system, and the ability to reduce chemical use. So Richard, Dr. Morita has helped us quantify the ability to use an LED at point of dispense. What we've seen is the ability in a very short period of time, only 3 minutes a day of one time, being able to prevent any bacteria or microbial or mold growth on the surface. A big part of this is being able to keep the dosage above 3 millijoules per centimeter squared, which ensures safety, but also has a prevention of retrograde contamination. We've been able to mock this up over a period of time in our lab. So on the top line, you'll see a UVC treated point of dispense nozzle. On the bottom side, you'll see growth over a 14-day period when touching occurs with certain black mold. There's one element where this type of exposure to black mold could lead to skin irritation, but also if not cleaned or treated, it will contaminate the water supply. There's many different applications that are useful for point source treatment at point of dispense. Healthcare setting, as I mentioned, hospitals, clinics, nursing homes, where you have a population that is immunosuppressed, the opportunity for a small amount of Legionella to cause Legionnaire's disease at point of dispense, or mold growth will have significant effects in a hospital or nursing home. The food and beverage industry, particularly the HoReCa industry, which people think of as restaurants, hotels, and public cafes. Mainly the risk here is that there is a larger population coming in and out using the water dispense product throughout the day. The risk of retrograde contamination, contaminating the system and causing transmissible sickness is a risk. And you'll see the same thing in public spaces, airports, public transportation, and schools. So big future opportunities are really in agriculture around drip irrigation or vertical farming. So using small amounts of drip water to grow crops has the ability of the whole water system to get disinfected or to grow microbes that can cause a problem both with plant growth, but also with the water system as a whole and causing risk to the humans operating it. The opportunity is to add a single UVC LED at the point of dispense, therefore not having splashback be nearly as big of a microbial risk. And then the last opportunity that we really see as an immediate application is in produce. So as you can imagine, in your local grocery store, there's plenty of misting locations, both for on-shelf food and also for climate control. If the water system lacks protection, the ability to mist Legionella, which could lead to Legionnaire's disease, as well as ensuring the quality of that water extends the shelf life of the vegetables, fruits that the mist is being used to prolong, leading to longer shelf life of consumables for the public. I don't know if you have anything else to add, Richard?
No, it's just slightly about the type of mycosis that occurs from that mold, Exophiala lecanii. The problem is that it is so painful. The skin itches so much, and even if the treatment regimen was to be started right away, it takes like a whole year of you taking medicine every day before you get your skin back to somehow normal. It would not be really that normal because it gets a little bit smooth, but it takes a whole year for you to get back.
So I think that the key takeaway is that water companies are changing and thinking about water conservation. They're thinking about that, everything from bottles, reduction of plastic bottles and going to reusable dispense locations where you go to a public space and fill up a reusable bottle. The healthcare industry is thinking about how to use high quality water to protect the immunosuppressed. And the agricultural industry is also thinking about water consumption with things like drip irrigation. All these are good, sustainable developments to be able to use less water, safer water. There's an opportunity now as we remove chlorine, as we use higher end filtration, for the system to grow microbial or mold risk from the inlet, from the outlet instead of the inlet. Most of our water treatment has been focused on the inlet. There's also the risk at the outlet. The good news is that UVC technology has developed enough that there's no longer a need for mercury. There's also no longer a need for a replaceable lamp on a yearly basis. There's the opportunity to use a single LED to protect this ingrowth in a variety of different applications. Britt, do we have any questions?
So we've had a couple questions come in. One was a clarification of what is CE compliance.
Yeah. So in each one of these standards, let's see. In each one of these standards, they refer to an exposure. A lot of them refer back to ACGIH. So CE compliance would be the ability to ensure the electrical system is safe So on these small systems, we can use potting and different compounds to protect the electrical components from shock risk. And then the other safety component is the exposure risk to UVC. So part of certain standards within RoHS and CE require you to ensure that both the material set can be exposed to UVC and also that the dose exposure is less than 3 millijoules per centimeter squared over the period of a day. So you're protecting the user from UVC exposure, and then you're protecting the user from shock.
And if I might add something there, it's actually acceptable to get exposure up to 10 millijoules per centimeter squared. That has been done extensively. There's extensive research on that. However, we are able to demonstrate that we can go for less than 10 at 3 millijoules per centimeter squared, and we are able to give very effective solution in this area.
Thank you for the clarification, Richard. I appreciate it.
Yep. Additionally, there was a question about like lifetime of the nozzle design concept that you showed.
Yeah. So it depends slightly on the on or off cycle. So it depends slightly on the consumption, how much the device is being used. But in standard usage where this is coming on 2 to 3 times a day, the product life will not be restricted. So this could be designed to last 10 years, 15 years. The LED life will be over 10,000 hours of on time. And because the LED is a solid state device, it can turn on and off without deterioration hundreds of thousands of times. So system design could be over 10 years.
Then I had one more question, and that was the magnitude of cost of these little POD devices.
Yeah, so it depends on volume and scale, but sub $10 US dollars. With some efficiency and scale and volume, it could be even significantly lower than that. One of the ideas is that in the water industry, the number of different aeration patterns or water flow patterns is large. So a lot of manufacturers have their own preference, and a lot of designers have their own preference. This type of design could be modified to use any of those, whether it be a 5-star, whether it be a standard aerator with a mesh screen. This type of design could be allowed for integration with any flow pattern.
Okay. Another question came in, and that is, can it run on a battery and at what voltage?
Yeah, short answer is yes. So it's anything above 7 volts, so a 12-volt battery can work. A single LED has a power consumption of about 4 watts in general. So we have some other projects where we run what we call water reactors in rural areas off batteries. And that has multiple LEDs. So a single LED can be ran off a battery. It's really about just battery sizing and design.
Another couple questions rolled in. One is, what is the largest volume of water pipe size that this technology can be applied to? So like how large of a nozzle, I guess.
Yep. So this is around a half-inch design. It really depends on the flow. The water flow is not as much as the important component, as much as the diameter of the nozzle itself. So 3/4 inch could probably work, maybe up to 1 inch. But just for clarity, the water is only getting treated very slightly because of the flow paths is once you get above, a liter per minute, you're only getting a small amount of the UV dose into the water. So the goal would be that you would treat the water with a different UV device, possibly at point of entry or farther up in the system, maybe all the way back into the municipal system. But this device would prevent any ingrowth from retrograde contamination on the outlet. So pipe size, the diameter of this could most likely go up to 1 inch. We haven't tested that, but it could. And really, it's more about the water flow than the pipe size.
Okay, and I had one more question roll in, and that's this seems like a solution for developed countries at $10 a piece. Do you see a path towards this in low income communities or for kind of a more of an outreach?
Short answer, yes. In a lot of these like smaller components, the volume can drive costs down pretty considerably. I mean, exactly. Kind of the pricing that it's more the costing. The costing that we were discussing is more for your typical, I don't know, 10,000 units of what you put out into the field, or less. In larger scale applications, there's certainly the opportunity to drive this cost down sub $5. And we do at Crystal IS, it almost feels like that was there for a plug. So we work with 2 projects, UV for Good in the Ukraine right now, where we help provide reactors to war-torn areas of Ukraine. And those reactors have the ability to run off of batteries, be deployed to remote locations. And then also another project we work with that Richard leads is called Maji Safi in Africa, in certain areas of Kenya. And UVC LEDs can be used off grid at relatively low cost for developing areas or areas that have water quality risks. The issue with this in those markets is that many times you also need microbial treatment on the incoming water supply. And depending on the flow rate, that cost component is what we're trying to drive down through some of these field and nonprofit efforts. Short answer, yes. Longer answer, we need to commercialize the design with some volume.
Awesome. I did have one more. It's other questions of integrated power generation using water pressure rather than batteries. Is this a common trend?
It's becoming common. So as the wall plug efficiency of LEDs increases, the ability to use a small inline water turbine to power the LED is certainly becoming more common. There's typically still some battery storage required, but for energy generation, yes, absolutely. I think as LEDs improve and as the cost of electronics continues to come down, we're probably pretty close to being able to have a standalone device that doesn't need external battery supply or energy supply. So I think we're running up against the time right now. So I think we will wrap that up. So you can reach out to us at Crystal IS, Dr. Marita, Patrick Eildinger, Britt Hafner is also on the call. If you have any questions, you can go to our website to learn a little bit more about UVC LEDs. And then this presentation will be shared, and feel free to reach out. Particularly Richard's very interested in this topic and has done a lot of research around how we can prevent retrograde contamination. Thank you for your time.
Thank you.